Hello everyone, today we're gonna start with Unit 10, Network Evolution, talking about optimum networks and modifying duties. A minimum network is just a starting point, not an optimum network necessarily. It is just a network that uses the minimum heating and cooling, and perhaps the minimum number of units for this minimum utility use. But at the same time, the topology can be too complicated. This can make for too much pumping cost and increased piping and instrumentation effort, including taking a lot of space. There can be very different heat exchangers area. Too large for some, too small for others. For too small heat exchanger, perhaps the recovery doesn't work. And this difference in the size of heat exchanger made for a difficult maintenance and having a lot of different spare part storage. The network can present also about operability, about control, difficult startup or shutdown. This leads to more manpower and more non-programmed shutdowns. Design is also a difficult trade-off, a compromise between safety, the investment, the operating cost, and operability. That requires a lot of experience and knowledge on the process. All these other considerations are not taken into account by the pinch design method, just the first and second principles, the minimum number of heat exchangers and the minimum temperature approach. So, after arriving to a minimum network, there is normally an optimization or improvement stage. And this means, in simple words, to modify the duty of heat exchangers, sometimes eliminating it, taking the duty to zero, sometimes creating some new heat exchanger, starting from a zero duty to a different one, and normally just changing the numerical value of the duty. During the optimization stage, we will not respect any pinch design rule. And if some of them becomes violated, a price must be paid. More utility will be needed if some heat cross the pinch or the number of heat exchanger is down the minimum. The problem is that modifying duties is difficult, because as the network is now tightly integrated, if you modify one duty, some intermediate temperatures or the duty of other heat exchangers can change. Temperature difference can become small, too small or negative, and the network can become out of balance. Follow this modification example. We want to change the duty of 6 to 400 kilowatts from 531 kilowatts. Then if we reduce the duty of 6, we are obliged to increase the duty of 7 to maintain the heating stream in balance. And we will have to reduce the duty of 5 in order to maintain 4 in balance. And increase the duty of 4 in order to maintain stream 5 in balance. On balancing stream 2, we have no more heat exchanger that will need some extra cooling. and we will have to reduce the duty of 3 to maintain stream 1 in balance, and increasing the duty of 2 to maintain cooling in balance, in such a way that stream 3, that has no more heat exchanger, rests unbalanced and some extra cooling will be needed. As you see, the consequences of changing one single duty are difficult to control. And these changes provoke unbalancing in streams or small or even negative temperature differences in heat exchanger. We would need tools to make this modification more controllable.